Let's first solve a simple question based on this formula. A 2 kg object is to be heated from 25 degrees C to 75 degrees C. Okay. Suppose its specific heat is some 2000 joule per kg per Kelvin. Okay. Calculate the heat required. Simple direct question. Solve it quickly. I got one answer as 2 into 10 power 5 joules, another as 200 kilojoules. Both are same. Okay, good. Right. Now, see, there is an assumption we are making when we use this formula delta Q is equal to ms delta T. Okay. Unknowingly, we'll be making that assumption. See, temperature is changing all the way from 25 degrees C to 75 degrees C. Okay. Yesterday, we discussed the definition of a calorie. One calorie is the amount of heat required to raise the temperature of pure water from 14.5 degrees C. Okay. To raise the temperature of 1 gram of pure water from 14.5 degrees C to 15.5 degrees C. Okay. For the same 1 gram of pure water, if you want to raise the temperature, let's say from 44 degrees C to 45 degrees C, the heat required will be slightly different. Slightly different. Okay. So for all changes in temperature, the amount of heat required is not the same. Okay. Even if the changes are equal, the amount of heat required practically will not be the same. Theoretically, you can assume it to be the same. Okay. So when you use specific heat here, 2000 joule per kg Kelvin, okay, per kg per Kelvin, for this entire temperature change, you are assuming that every 1 degree change requires the same amount of heat. Okay, that is an indirect or yeah, that's an indirect assumption that we are making. Fine. As I said yesterday, unless otherwise specified, that is how you are supposed to solve problems. Okay. But suppose you are given a situation like this. Let's say there is an object whose mass is some 5 kg and its specific heat varies with temperature. Okay. And how does it vary with temperature? Let us take it as some 2000 into 1 plus 0.1 T, where T is the temperature of the object in Kelvin itself, let us take. Okay. Or wait. Let's take it in Celsius degree. Degree Celsius. Okay. That means based on its temperature, the specific heat will change. And based on its temperature, according to this equation, observe this equation carefully. 2000 into 1 plus 0.1 T, units are SI units. So as the temperature increases, the specific heat increases. What does that mean? See, we discussed the definition of specific heat yesterday. Basically, it's the heat required to raise the temperature of unit mass of a substance by 1 unit. If specific heat is increasing, that means you need more heat to bring about a change of 1 degree in the temperature. Okay, as the temperature increases. So for this system, specific heat is not constant. Right. Now, how to solve this kind of problem? Suppose you want to find out how much is the heat required to raise the temperature of this system from, let's say, some, okay, 20 degrees C to 40 degrees C. Now, temperature to temperature, the specific heat will vary. So, can any of you give me an idea what to do?
So dq equal to ms dt.
Okay, good. You'll have to integrate. You'll have to use the differential form of the equation. Good, very good. Both of you have given the same answer. Fine. So you'll have to write it this way now. dq is equal to ms dt. Okay. Understand what this means. When you write this equation, what you are indirectly saying is for small amount of heat supplied and for small temperature changes. Okay. How small you can't even tell. Okay. dt value you cannot tell. but it's non-zero. It's a non-zero change in temperature. So when you are writing an equation like this, what you are indirectly saying is for such small changes in temperature, specific heat can be assumed to be constant. Okay. So dq is equal to ms dt. Then if you want to find out the total amount of heat required, you'll have to integrate both sides. Good. Integral dq becomes the total amount of heat supplied, delta q is equal to mass of the object is constant, integral s dt. Now you write the equation for specific heat here. I mean, you substitute that equation, you integrate, you can find out the heat supplied. Okay. Uh, you solve this problem later, but this is how you proceed in case specific heat is variable. And usually for solids and liquids, specific heat will remain almost the same. Okay, it won't undergo significant changes with temperature, but for gases, specific heat depends on the process that the gas is undergoing. Okay, and it can very well depend on its temperature also. Okay, it can easily vary based on its temperature, pressure, volume. You learn in thermodynamics, okay, which is the next part of this chapter. Okay, next, suppose there is an isolated system. Can any of you tell me what we mean by an isolated system? And when we say isolated here, we are talking about thermal isolation. Okay, so a system is thermally isolated. What does that mean? Basically, what does isolation mean? Isolation means keeping something separate, not allowing it to interact with anything else. Okay, that is what is isolation. So suppose there is an isolated system. Let's say there are two objects in this isolated system. Fine. When we say the system is isolated, it means it is not allowed to exchange heat with the surroundings. That is what we mean by thermal isolation. No heat exchange with surroundings. So it cannot take heat from the surroundings. It cannot release heat also to the surroundings. Okay, that is what we mean by an isolated system, right? Now, with the surroundings, the system cannot exchange heat. That's okay. But among themselves, they can exchange heat. No, the orange object can give heat to the blue object, or the blue one can give heat to the orange one. Fine. And heat basically is that kind of energy which flows from an object of high temperature to an object of low temperature, as long as there is a temperature difference. Okay. So suppose this orange object is at some 50 degrees C when you put it in that isolation box, okay, insulated box, you can say. And let's say the blue object is at some 30 degrees C when you put it in that insulated box. Now, orange object being at higher temperature loses heat. Fine. The blue object being at lower temperature takes heat. So 50 degrees C will keep coming down, 30 degrees C will keep going up until their temperatures match. When their temperatures match, then there won't be any net heat exchange after that. Okay. When the temperatures match, we say that the system is in thermal equilibrium. So all this is what you call as principle of calorimetry. In an isolated system, the hotter objects lose heat and the cooler objects gain heat. The heat lost by the hotter objects is equal to heat gained by the cooler objects. Fine. And this heat exchange will keep happening till the temperature becomes equal. Okay. Till the objects attain thermal equilibrium. So let me just mention the statement here. Heat lost by the hotter objects is equal to heat gained by the cooler objects. Okay. And remember, this heat exchange will happen till they attain thermal equilibrium. Fine. Now, we discussed this formula, delta Q is equal to Ms delta T. Remember, in this formula, delta T is temperature change of a given object, of one object. So basically, it is final temperature of the object minus initial temperature of the object. You will have to write it this way only. You cannot interchange. You can't write it as initial minus final. Okay, delta T means temperature change. Now, if delta Q is positive, delta T will be positive. And remember, delta Q here is the heat supplied to the object. You can also say it is heat absorbed by the object. Okay, these are terms that they use in questions. You should not get confused by them. So when you give heat, temperature increases. That is what we are saying or meaning by this equation. Okay. Suppose you want to write an expression for heat lost by an object. This delta Q is heat gained by the object. Okay. Can any of you tell me how you will write the expression for heat lost by an object? The formula for heat gained is ms delta T. What will be the formula for heat lost? Heat lost is just negative of heat gained. That's all. Okay. So heat lost by an object is negative of heat gained by the object. So it becomes minus ms delta T. That is how you are supposed to write heat lost. Okay. Now, why are we discussing this? Because to apply the principle of calorimetry, you need to know how to write an expression for heat lost by a system. Fine. Heat lost by one object is equal to heat gained by the other. There is another way also of putting this statement. See, if see one is losing heat, one is gaining heat. So one delta Q will be negative, one delta Q will be positive. But if you put them together, if you add them, total delta Q will be zero, no? So principle of calorimetry can also be stated like this. In an isolated system, okay? And this way it is much easier to apply. In an isolated system, net heat gain is zero. What we mean is, suppose there are three objects in an isolated system. Heat gain of the first object plus heat gain of the second object plus heat gain of the third object will be zero. When you write an equation like this, automatically some of them will be positive, some will be negative, but all of them put together will be zero. So it is better to use it this way, okay, or apply it this way. Let's solve one question based on this. Let's say there are two liquids, A and B. A is at initially at 40 degrees C. Specific heat of A, let's say some 1500 joule per kg per Kelvin. B is initially at maybe 60 degrees C. Specific heat of B, let's say is 2000 joule per kg per Kelvin. Okay. Now, how much of A and B are there? That also I'll mention. Mass of A, let it be some 2 kg. Mass of B, let it be 4 kg. Okay. So 2 kg of substance A, which is at 40 degrees, is put together with 4 kg of substance B, which is at 60 degrees. Okay. System is isolated. Now, the one at 60 degrees will lose heat, the one at 40 degrees will gain heat until they finally attain a common temperature. I want you to find out that common temperature. Calculate the temperature at thermal equilibrium. Okay, you have to assume the system is isolated. Fine. Do this, all of you. I'll give you 2 minutes. Okay, I got one answer as 54.55 degrees C. Fine, let's see. See, this is an isolated system. Heat lost by the hotter objects is equal to heat gained by the cooler ones. You can write an equation that way. Otherwise, you can also write net heat gained by all the objects is zero. Okay, so that is the way, I mean, it is safer to solve. So heat gained by A plus the heat gained by B should be 0. One of them will be positive, one will be negative. Okay. How do you write heat gained by any object? Ms delta T. Okay. So now you don't have to bother about whether it should be plus Ms delta T or minus Ms delta T. You can directly write Ms delta T. Okay. Now our aim is to calculate the final thermal temperature at thermal equilibrium. Let that temperature be T in degrees C itself. Okay. Now delta Q for A will be written as mass of A, specific heat of A multiplied with change in temperature. Change in temperature is always final temperature minus initial temperature. Then that for B will be written as mass of B, specific heat of B multiplied with change in temperature. Final temperature minus initial temperature of B. And this sum should be equal to 0. Now see, one is at 40, the other is at 60 initially. Then the common temperature that they attain will be somewhere between 40 and 60. Greater than 40, but definitely less than 60. Now if it is greater than 40, that means for A, the delta Q will be positive. But if it is less than 60, that means for B, delta T will be negative. That is how this equation will become correct finally. Okay. So now you just have to substitute the numbers. Mass of A is given as how much? 2 kg, the other is 4 kg. 2, specific heat of A is 1500. Final temperature is unknown, initial temperature is 40. Plus mass of B is 4 kg, specific heat of B is 2000. Unknown final temperature minus initial temperature 60 equal to 0. Just solve this equation, you will be able to tell the temperature. Okay. Vanilla, where were you stuck? Why were you not able to answer? Pawan, you also. Why were you not able to answer? Okay, fine. If you have any doubts, you can ask. Okay. And the same procedure you can follow with any number of objects or liquids. Okay. But there is an assumption we are making here. See, temperature changes are happening for these materials. No. Usually, when temperature change happens, or not temperature change, sorry, heat is being lost by one of them, heat is being gained by the other one. Usually, when an object loses heat or gains heat, it is quite possible that the state of the object changes. It could convert from liquid to gas. Okay, if it is gaining heat, it could convert from gas to liquid, or it could convert from solid to liquid, liquid to solid also, depending on how much heat is being supplied. Okay, we have ignored those changes. I told you yesterday, you can use a particular specific heat value only for a particular state of that material. Okay, solid state, it will have one specific heat. Liquid state, it will have a different specific heat. Significant difference will be there. Okay, so if you are using one particular specific heat, you are assuming that there is only one state. Okay, it is that particular object or material is not undergoing a change of state. That assumption is being made. Okay, let us now discuss how change of state happens. Okay, and how to do calculations based on that. Okay, let's take example of ice itself. See, generally, a material can stay in solid form, okay, at temperatures less than or equal to the melting point temperature. It can be in solid form exactly at melting point temperature also, or at a temperature less than that. Okay. For example, if it is ice that you're talking about, it should be less than or equal to 0 degrees C. Okay. You can't expect to find ice at a temperature more than 0 degrees C. Okay. Or you can't expect ice to exist at a temperature more than 0 degrees C. Okay. Generally, see, there are always exceptions. By adjusting pressure and all, you can have ice at temperature more than 0 also, but we are not discussing those. In your syllabus, you don't have all that. Okay. So usually material exists in solid state at temperature less than or equal to melting point. Okay. Then in liquid state, the material can exist from temperatures equal to melting point to the temperature equal to boiling point. So melting point less than or equal to the temperature less than or equal to the boiling point. In this range of temperatures, the material exists as liquid. So if it is water that you're talking about, it can exist in this form, in water form, from temperatures 0 to 100. Okay, we know boiling point of water is 100, but yes, again, by adjusting pressure, you can change the boiling point. Okay, that is the idea in a pressure cooker and all. Anyway, we won't consider all that for now. Then, in gaseous state, okay, the material can exist when its temperature is greater than or equal to the boiling point temperature. Okay, if it is steam that you're talking about, steam is the gas form of water. Okay, so the temperature has to be more than or equal to 100 degrees C. This is just an example. Different materials will have different melting points, boiling points. Okay, just a moment. Fine. Assume there is a certain amount of ice in a container. It's a closed container, but it's not insulated. You can supply heat. Okay, it's closed. Fine. Now, assume the ice is at a temperature less than 0 degrees C. So basically, it's at a temperature less than the melting point. Okay, if temperature is less than melting point, it will definitely exist in solid form. Okay. Now you supply heat to it. Okay. What will happen? Anyone? If you supply heat, what will happen? Material is at a temperature less than the melting point temperature, and you supply heat. Generally, if you supply heat, temperature rises. Okay. So since the temperature is less than melting point temperature, it will gradually increase and reach up to the melting point temperature. Okay, and increase up to melting point. So it can stay in the same solid state. Okay, till its temperature becomes equal to melting point temperature. So initially it was in solid state. Till the temperature becomes equal to melting point temperature, it will stay in solid state itself. Okay, you can do the reverse also. At melting point, if the solid is at melting point and you remove heat, it will go to a temperature less than melting point. That's all. Right. Now suppose you have supplied enough heat and the solid has just reached the melting point temperature. Now if you continue supplying heat, okay, its temperature cannot rise any further in this state, because if you take example of ice itself, at normal temperature and at normal pressure, ice cannot exist at a temperature more than 0 degrees C. So if you raise the temperature any further, molecular vibrations will increase so much that it cannot stay in solid form anymore. It converts to liquid. But when that conversion is happening, okay, when ice converts to liquid, okay, when ice converts to water, temperature change will not occur. Okay, ice at 0 degrees will convert to water at 0 degrees. Gradual conversion will happen. Okay, you will need to supply a significant amount of heat. So if you supply heat to ice, which is at 0 degrees, or generally if you supply heat, okay, green indicates supply. Okay, if you supply heat to a solid which is at melting point, then without a change in temperature, it will convert to liquid. Fine. And in your syllabus, as far as your syllabus is concerned, we will make this assumption that until the entire solid converts to liquid, no change in temperature happens. Now, in a real life situation, it's possible. Suppose there is a lot of ice in a container and you start heating that container. Okay. Then it's quite possible that in one corner of the container, ice has melted into water and water's temperature has gone above zero also, maybe some 5 degrees, 6 degrees. And on the other side of the container, same container, some ice is still existing. Okay, so in a real life situation, when you take a large container, it's quite possible that different parts of the material are at different temperatures. Okay, but as far as your syllabus is concerned, we will assume that until the entire solid converts to liquid, temperature doesn't rise anywhere. Fine. So when you supply heat to a solid which is at melting point temperature, it will convert to liquid at melting point temperature. For example, if you take water, it turns to water at 0 degrees C. Okay. Now, if you continue supplying heat, or this same step, if you do the reverse, okay, if liquid is at melting point temperature and you remove heat, red indicates removal of heat, then obviously it will undergo freezing. Okay, melting opposite is freezing. Fine. Now, if liquid is at melting point temperature and you supply heat to it, what will happen? Its temperature will rise. Okay, and liquid's temperature can be risen up to or till the temperature becomes equal to the boiling point temperature. So if you supply heat to a liquid which is at melting point or greater than melting point, also you continue supplying heat, it can go up to boiling point temperature, not beyond that. Okay, there is a limit to the temperature at which up to which it can exist in liquid state. So it can go up to, in case of water, it can go up to 100 degrees C. Okay, that is basically the boiling point. There, no change of state happens. So once the solid has completely converted to liquid, the liquid's temperature starts rising. Okay, that is how we assume as far as your syllabus is concerned. Okay. Reverse is also possible. You remove heat, liquid's temperature will decrease till it goes down to melting point. Okay. Suppose the liquid has reached boiling point temperature. Continue supplying heat. What will happen? It will have to boil now. It has no other choice. So if it is water, it converts to steam. So liquid converts to gas now when you supply heat. And when liquid converts to gas, the new gas or the gas that is formed, just formed, will be at a temperature equal to boiling point temperature. So a change of state is happening. Here also we make the same assumption. Until all the liquid converts to gas, no change in temperature happens. Heat is being supplied, but no change in temperature happens. Okay. And the reverse. If you remove heat, gas condenses into liquid. Okay. Vaporization, reverse process is condensation. And gas which is at boiling point temperature, if you continue supplying heat to it, then it can go to any higher temperature. Okay. One more step also we can draw. Fine. Practical limitations will be there, but theoretically you can take a gas to any higher temperature. Okay. Any higher temperature than the boiling point. Okay. So these are the different stages that a material undergoes when you supply heat or remove heat from it. Okay. Now, while being in the same state, if you supply heat, its temperature will rise. If you remove heat, its temperature will decrease. So when state change is not happening, you can use this equation. For example, solid to solid. Okay, in solid state itself, when temperature is changing, you can use delta Q is equal to M into specific heat in the solid state, delta T. Okay. Then in liquid state itself, if temperature change is happening, you can use delta Q is equal to M into specific heat of liquid multiplied with delta T. In solid state, liquid state, specific heats will usually be different. Okay. Same in gaseous state also. Okay. Without change of state, if temperature change is happening, you will use M into specific heat of gas delta T to find out how much heat is absorbed or released for a certain temperature change. But see, when change of state is happening, there is no change of temperature. Okay. When it goes from solid to liquid, temperature does not change. When it converts from liquid to gas, also temperature does not change. But heat exchange is necessary. It should absorb heat to go from solid to liquid or liquid to gas. It should release heat to go from gas to liquid or liquid to solid. Fine. So delta Q should be non-zero during state change, but delta T should be zero. Then you can't use this equation delta Q is equal to ms delta T for state changes. Okay. Obviously, you cannot use because delta T is not there during change of state. There's no change on temperature, but delta Q will be there. Okay. Positive or negative. So for state changes, what we do is we use this equation delta Q, or you can think of it this way. State change requires heat. Okay. For example, if you want to melt ice to water, you'll need to supply heat. Now, the amount of heat you supply to melt ice definitely depends on how much ice you want to melt. Okay. So, the amount of heat required for a certain change of state to happen depends on how much material is present. And it obviously depends on the material also. To melt 1 kg of ice to water, you may require a certain amount of heat. But to melt 1 kg of, let's say, steel, you may require a different amount of heat. Okay, so it definitely depends on the material, molecular properties. Okay, so the heat required for state change depends on the amount of material that is present, depends on the mass, and it also depends on the type of material. Okay, so the equation goes like this: delta Q is equal to mL, where L is what we call as latent heat. Now, for solid liquid conversion or liquid solid conversion, we use latent heat of fusion. LF stands for latent heat of fusion. You can use the same equation for forward process as well as backward process. In one case, delta Q will be positive, in another case, it will be negative. Okay. And for liquid gas conversion, okay, when that boiling process happens, you use delta Q is equal to M LV, okay, where LV stands for latent heat of vaporization. Right. So to find out the heat absorbed by a material or released by a material during change of state, this equation has to be used. Delta Q is equal to ml. Okay. Let's solve some problems based on this. And okay, before solving the problem, we need to discuss an important graph. Basically, the graph of temperature of the material, okay, as a function of heat supplied to it. So on the y-axis, let's consider temperature. In any unit you can take, usually we take in degrees C. On x-axis, let's say there is heat supplied. Okay. Assume the material is initially in its solid state at a temperature less than the melting point temperature. Let us mark those melting point and boiling point values here. Let's say this temperature is the melting point temperature and this is the boiling point temperature. Obviously, boiling point will be higher than melting point. Okay. Suppose the material initially is at some temperature like this, clearly less than the melting point temperature. Now, if the temperature is less than melting point temperature, it will be in solid state. Okay, it has no other choice. Now you supply heat. If you supply heat to an object which is at temperature less than melting point, first its temperature will rise. Till what point will it rise? Till it reaches the melting point, it will rise. And how are heat and temperature related? Heat supplied delta Q when no change of state is happening, when change in temperature is happening, delta Q is ms delta T. Heat supplied is proportional to change in temperature. Change in temperature. When heat supplied is proportional to change in temperature, it means the graph will be a straight line. Generally, when change in y is proportional to change in x, the yx graph will be a straight line. Okay. So linearly, its temperature will increase till it reaches the melting point temperature. Okay. Now melting point is around this level. So in solid state itself, its temperature rises as you supply heat. Okay. So what is the equation governing this process? Delta Q is equal to ms delta T, where S is the specific heat for the solid state. Okay. As I mentioned, so a specific heat can vary from state to state. Okay. Suppose the solid has reached melting point temperature. Okay. S stands for solid. You continue supplying heat. Okay. So X value will continue increasing. But when it is at melting point temperature and you continue supplying heat, melting takes place, change of state takes place. And while change of state is happening, there won't be a change of temperature happening. Okay. So remaining at the same or staying at the same temperature, melting point temperature, the solid absorbs heat and converts to liquid. So the graph will be a line parallel to x-axis because y coordinate temperature is not changing. So solid converts to liquid. Okay. So here the governing equation is delta Q is equal to M specific heat of solid delta T. Then for solid liquid conversion, the governing equation will be delta Q is equal to M L F, latent heat of fusion. Okay. Suppose all the solid has converted to liquid. Then you continue supplying heat again. Now, when liquid is at melting point temperature and you supply heat, its temperature rises. Then again, the equation governing the process will be delta Q is equal to Ms delta T. Temperature will vary linearly with heat. But the specific heat in solid state is not same as specific heat in liquid state. Okay. So, like if you look at this equation, delta Q is equal to Ms delta T, Ms, okay, temperature change is on the y-axis. It's like delta y. This is delta x, no? So you can write delta y is equal to 1 by ms delta x. Okay. So this here is the slope. Generally, you write y is equal to mx plus c, no? So the coefficient of x is what you take as the slope. Here, the coefficient of delta x is taken as the slope. So if specific heat is more, the slope will be less when temperature is on y-axis and heat is on x-axis. Okay. Slightly mathematical coordinate geometry. Okay. So slope of the line, okay, or slope of the graph depends on the specific heat. Obviously, on how much mass also it depends, but we are assuming mass remains constant here, then it depends on specific heat. Okay. So liquid at melting point is supplied heat. So what will happen? Its temperature will rise and it will rise linearly. Okay. The slope need not be the same as I mentioned. It depends on the specific heat. So let's say liquid's temperature rises to boiling point temperature. Okay. The equation governing this process will again be delta Q is equal to Ms delta T. But this time you will have to take specific heat of liquid. Okay. Right. Once all the liquid reaches the boiling point temperature, continue supplying heat. It will stay at that temperature and convert to gas. Okay. How much heat is needed to convert to gas depends on the latent heat. So liquid converts to gas, and the equation for that step will be delta Q is equal to mLV, latent heat of vaporization. And once it converts to gas, after that, if you continue supplying heat, its temperature can increase to any extent. Okay. And we'll assume it's a linear increase itself. Okay. Fine. So solid at less than melting point can go down to any temperature, 0 Kelvin also theoretically. Gas at temperature more than boiling point can go up to any temperature. Okay. After that, the equation governing the process will be delta Q is equal to M specific heat in gaseous state delta T. Okay. Questions based on this graph are quite common. They can give you a graph like this and directly ask you what is melting point, boiling point, or they can give you the coordinates and ask you what is the specific heat and such things also. Okay. Uh, let's see. Let's try one problem based on that. Assume the melting point is for some material. Let's say melting point is 40 degrees C and boiling point is 100 degrees C. Okay. I have given you melting point and boiling point, so I can ask you for specific heat in liquid state. Okay. Let's say the heat supplied till here was some 4000 joules, and here the coordinate is say 5000 joules. Just an example that I'm taking. Okay. And assume the mass of the object is some 2 kg. So when the change in temperature of a 2 kg object was plotted as a function of heat supplied, this is the graph we got. Okay. Tell me the specific heat of this object in liquid state. Solve this quickly. Okay, fine. It's a direct question. You need specific heat. Specific heat is delta Q divided by M delta T. That's all. Now we need specific heat in the liquid state. Now in liquid state, the material is going from this temperature to this temperature. When heat changes from 4000 to 5000, so delta Q is 1000. That's the amount of heat to be supplied to the liquid. How much mass is given? 2 kg. And how much temperature change is it undergoing? 40 to 100 is 60-degree change in temperature. That's all. 4 25, 2 into 6 is 12, 3. 25 by 3 is the answer in SI units. Okay. Joule per kg per Celsius degree or joule per kg per Kelvin. It's the same, right? So you can like if other values are given, if other coordinates are given, you can find out latent heat of fusion, vaporization, specific heat in gaseous state, solid state, all those things. Okay. And you may even be asked, what is the slope of this graph, this part of the graph, this part of the graph, and so on. So as I said, slightly mathematical. Slope basically is the ratio of change in y coordinate to the change in x coordinate, y2 minus y1 by x2 minus x1. So basically here slope on y-axis we have temperature, x-axis we have heat. So for this graph, okay, when you take temperature on y-axis, heat on x-axis, slope is change in temperature by the heat supplied. Now we know delta Q is ms delta T. So delta T by delta Q becomes 1 by ms. So when the graph is drawn in this form with temperature on y-axis and heat on x-axis, then slope is 1 by ms. They can even reverse the coordinates. Okay, exchange the coordinates. They can show you heat on the y-axis and temperature on the x-axis. Okay, then slope of that kind of a graph will be delta Q by delta T, which is directly equal to ms. Okay, so you need to be careful. You have to observe properly what is given on x-axis, what is given on y-axis. Based on that, you can answer all the questions based. Okay, now let's include latent heat in our equations. You all can note down these values. Remember them. We'll be using them frequently. Specific heat of ice, okay, is 0.5 calorie per gram per Celsius degree. This is not in SI units, okay, but for ice it is 0.5. For water, it is 1 calorie per gram per Celsius degree. But that is by definition of calorie. We had discussed that in the last class. Then specific heat of steam. Steam is the gaseous form of water. Uh, just a moment. Let me look up the value. Okay, let me give you this as a question. Specific heat of steam. Okay, I got the answer on Google as 1.996 kilojoule. Kilojoule means into 1000 joules per kg per Kelvin. Okay, 1.996 will round it off to 2. So specific heat of steam in SI units is 2 joule per kg per Celsius degree, or per Kelvin also you can write. Convert it to calorie per gram per Celsius degree, and for converting, use this rough approximation that 1 calorie is approximately, take it as 4 joules. Okay. Exactly it is 4.18. Let's assume it is 4 just for convenience. Okay. So use this and express specific heat of steam in calorie per gram per Celsius degree units. Do this quickly, all of you. Small mistake here. It's not 2 joule, it is 2000 joule. 2 kilojoules actually. Yeah. Convert it to calorie per gram per Celsius degree. Okay, I got one answer as 0.5 calorie per gram per Celsius degree. Fine. I think that is correct only. 1 calorie is 4 joule, so 1 joule will be 1/4 of a calorie or 0.25. We'll use that directly. So it becomes 2000 into joule is 1/4 of a calorie, and kilogram inverse. Kilogram is 1000 gram. Okay. So it becomes 10 power minus 3 gram inverse. Okay. Calorie per gram per Celsius degree. That's all. So 1 by 2 effectively close to 0.5. Okay. So specific heat of steam and ice approximately the same. Next, latent heat of fusion. Okay. That means for conversion of ice to water or water to ice, the latent heat you use will be 80 calorie per gram. See, delta Q is equal to ml. L will be delta Q by m. Heat per unit mass, calorie per gram. In SI units, joule per kg. Okay. And latent heat of vaporization means water to steam and steam to water conversion is 540 calorie per gram. Okay. So keep a note of these values. We'll be using these values while solving problems. Okay. Try this question first. Simple. Let's say there is 20 grams of ice. Ice can exist at any temperature less than or equal to 0 degrees. So it is at minus, let's say, 5 degrees C. Now you need to convert it to water at plus 20 degrees C. Okay. Obviously, to convert ice to water, you'll have to supply heat. Okay. And temperature change is also happening. You'll definitely need to supply heat. Temperature increase is happening. Find out the heat required. One of you quickly tell me, can we directly use delta Q is equal to ms delta T to find out heat required for this conversion?
No, sir.
Definitely not, because ice has one specific heat, water has a different specific heat. And in between, there is also change of state happening from ice to water. That step requires a different equation. Okay. So, how will you go about solving this? Any idea, anyone? How to proceed? You need to assume that heat is gradually supplied to ice which is initially at minus 5 degrees C. So ice which is at minus 5 degrees C, if you supply heat, since the temperature is less than melting point temperature, without undergoing a change of state, the temperature will first reach the melting point temperature. So ice at minus 5 should get converted to ice at 0 degrees first. Without change in state, temperature change will happen. So there you will use the equation delta Q is equal to m into specific heat of ice into delta T. Okay, once all the ice reaches 0 degree temperature, then imagine continuing supplying heat. Ice at 0 converts to water at 0. Okay, as I said, in your syllabus, we'll assume all the uh, material, whatever is present, undergoes state change at the same time. Sorry, not same time, at the same temperature. Okay. And till all the material undergoes the change of state, temperature changes won't happen. Now, when ice is converting to water, change of state is happening. There you will have to use the equation delta Q is equal to mLF, latent heat of fusion. And then as heat is continued to be supplied, water temperature can rise to 20 degrees or how much ever is necessary according to the question. There again, you will use the equation delta Q is equal to ms, specific heat of liquid or water, multiplied with delta T. Okay. So the total heat that you will need to bring about this conversion is the sum of these three heats. Okay. So whenever any conversion is happening, whether it's temperature change, state change, or a combination, you'll have to imagine it like this. Heat is gradually supplied. What are the different processes that occur? Okay. Calculate this quickly, all of you. Okay. I got one answer as 2050 calories. Okay. Let's see. Anyway, we don't have too much. Okay. How much ice is given? 20. See, that 20 grams stays the same. When ice gets converted to water also, it's 20 grams only. Water converts to water at 20 degrees also, it's the same 20 gram. Okay, so in all steps, the mass is 20 grams itself. Specific heat of ice is 0.5 calorie per gram per Celsius degree. And the change happening here is 5 units. From minus 5, it is going to 0. So the change in temperature is 5. So 0.5 into 5. Okay. 1050 calories for this. Next, when ice converts to water, okay, 20 grams of 20 grams of ice, latent heat for ice water conversion is 80 calorie per gram. 20 into 80, 1600 calories. In the last step, the same 20 gram, now it's in water state. Specific heat of water is 1 calorie per gram per Celsius degree, and the change in temperature we want is 20 degrees. 20, 400 calories. Fine. The sum of all of them, the answer is 2050 calories. Good. Okay. Just a moment. Now see, here some material was given to you and you were asked to find out what is the heat required to convert this material to something else. Okay. Ice at minus 5 degrees to water at 20 degrees. These steps you will write, that's fine. You can do the reverse also. Okay. To convert ice at minus 5 to water at 20, you have to supply 2050 calories. To do the reverse, you'll have to remove 2050 calories from the system. Fine. So questions like this are also quite easy to solve. The difficult questions in calorimetry are the ones where state change is happening and there are two initial substances that are given to you. For example, you know that if you put ice in water, okay, let's say water is at room temperature and you put a cube of ice in it, ice melts. Okay, ice, let's say it is at less than 0 degrees, ice melts. Finally, you will find it in water state only. Okay, and see, there are variations also possible. Water also can convert. If you put a drop of water on ice, no, the drop will freeze. Okay, on a large amount of ice, if you put one drop of water, the drop of water will convert to ice. So that is also possible. Lot of water you put ice, ice converts to water. Lot of ice you put water, water converts to ice. But if they are balanced, okay, let's say a certain amount of ice, certain amount of water, finally you can have a mixture of both also. Okay, so those kind of questions are the difficult questions. So let's fine. I want you all to solve one problem before we get into those kind of questions. Just a moment, I'll give you the question. Let's say there is 20 grams of ice at minus 10 degrees C. Okay. Uh, Suppose we want to convert this ice to water and we want to convert this ice to water at 0 degrees. So ice at minus 10 should become ice at 0, then should convert to water at 0 also. So some heat has to be supplied. Now I can directly ask you how much heat is required for that, but indirectly I can ask you a question like this. How much water, okay, at let's say the water is at 5 degrees C. How much water at 5 degrees C must be added to melt all the ice? Okay, we just want to melt the ice. Means we want to convert it to water at 0 degrees. That's all. Okay, fine. So there is 20 grams of ice at minus 10 degrees. You have to find out how much extra water should be added to it such that the ice comes to 0. And after it comes to 0, the process should stop. The conversion should stop. That means this added water that is there, this should also go down to 0 by the time ice melts. Okay, because when ice melts, it will be at 0 degrees. No, this water will be losing heat, ice will be taking that heat in the process of temperature rise and melting. Okay, so one side of the system loses heat, the other side of the system gains heat. Finally, when will the exchange of heat stop? When they come to thermal equilibrium. Now what do we want? We want the ice to melt. Ice to melt means it should come to 0 degrees and stay in water form. At that time, okay, by the time ice converts to water at 0 degrees, this water at 5 degrees also should go down to water at 0 degrees. Then no further heat exchange will happen and the conversion will stop. Okay, so that is the idea here. Heat lost by this water should be equal to heat gained by the ice. So write an equation based on that and find out how much water at 5 degrees is needed. Okay, you assume the mass is m, calculate m. Do this all of you, I'll give you 2 minutes. If any of you are running late for school, college, you can go. Let's see. See, we just want to melt all the ice. Okay. This also has a meaning. That means final temperature of the entire system should be 0 degrees C and final state must be water. Okay. Now we'll first find out how much heat is needed to convert 20 grams of ice at minus 10 to water first. Okay. So first ice at minus 10 should be converted to ice at 0 degrees. For that, we'll have to use ms delta T. 20 specific heat of ice 0.5 will give answer in calories itself. I mean, it'll get cancelled anyway. And from minus 10, we have to take it to 0 degrees. So that's a change of 10 units. Plus, once ice reaches 0 degrees, it should get converted to water at 0 degrees. That can be calculated. The heat required for that can be calculated by using ml. 20 grams of ice, latent heat of ice water conversion is 80. Okay. So this is the amount of heat required by the ice to melt. And where will this heat come from? The water at 5 degrees has to supply heat. But water at 5 degrees, as it supplies heat, its temperature will keep coming down. So by the time ice melts to water, the temperature of water at 5 degrees should come down to 0 degrees. Then no further heat exchange will happen. Okay, and that is what we want finally. Okay. Now, water at 5 degrees, if it converts to water at 0 degrees, the heat that it releases, you can use ms delta T. We don't know how much water is there. Specific heat of water is 1. Temperature change. Now, we are writing heat lost by water. How do you write heat loss? Minus of ms delta T. Okay, so I'm writing ms minus of delta T. So final initial temperature minus final temperature. So heat lost by water is 5m. Heat gained by ice is this much. How much is this? 0.5 into 10 is 5, 520 is 100, 1700. Okay. So the heat required by the ice to undergo this conversion is 1700 calories. The heat which water can release in this process is 5m calories. That's all. You just have to balance these. You'll get mass from there, 340, correct. Okay. Fine. So we'll stop it here. Practice a few problems based on these. And tomorrow's class, we will discuss how to calculate heat in those cases where like where the final temperature is also unknown. Okay. Like for example, here in this question, you were given that ice is 20 grams, temperature of ice is given, final state and temperature were given to you. Okay. You just need to melt the ice. Means final temperature has to be 0. It has to be in water state. So we were able to write equations relatively easily. Now you can even be asked, like, let's say some 100 grams of water. Why is it writing this? Let's say some 100 grams of water is put along with this ice. Finally, what will you find? Will there be ice? Will there be water? At what temperature? So there the state will not be known. Temperature also will not be known. Okay. How to solve those kind of problems? We'll see in tomorrow's class. Okay. Thank you all. We'll continue tomorrow.